Okay, let's look at an example of a simple inductor problem and go through and do some calculations for voltage and power and energy. And so in this case, I've got an inductor connected to a current source, and to make this interesting, I'm going to assume this is a time-varying current source that has a value of 10 times t times e to the minus 5t amps for t greater than or equal to 0, but just equal to 0 for t less than 0. So if we were to actually go through and plot what this current looks like, we'll see something shaped like this. And at 0.2 seconds, we will find that the current reaches a maximum value of about 0.736 amps. And then as t increases, the exponential term begins to dominate, and then the current just rolls off. So let's go through, let's calculate voltage. So voltage will be equal to L di dt. And if I use the chain rule to take this derivative, multiply times L, what I'm going to get is this will be equal to e to the minus 5t times 1 minus 5t volts when I take that derivative. And if I plot that, I'll get something that looks like this. Where the voltage will jump up to a value of 1 volt, and then will decay down until it hits 0.2 seconds. And then we'll see this kind of behavior as it decays away. So once again, we will see an interesting kind of behavior based on both the exponential and the t. So it starts off, e to the minus 5t is just equal to 1. And so at time t equals 0, we just have a value of 1 volt. And then we're going to find this thing decreasing down, down, becoming negative as the minus 5t term dominates, and then rolling off towards 0 as the exponential term dominates. So we get something that looks like this. So from here, I of t and v of t, I can now go through and I can do some more calculations. First of all, I can find the power. So the power, which is just equal to I of t times v of t, if I take these equations here and multiply those through and simplify them, what I'm going to get is this is equal to 10t minus 50t squared times e to the minus 10t watts. And what you will find if you look for the maxima and minima of this function, and you can of course do that by taking the derivative and setting it equal to 0, which incidentally is very easy to do in Mathematica or a piece of software like that, Mathematica or MATLAB. But what I'll find is this is equal to 0.231 watts at t equals 0.0586 seconds. It's also equal to minus 0.0794 watts at t equal 0.341 seconds. So what this is telling us is we're going to maximize our power, positive power, power is being absorbed somewhere here in this region. So if you look at this, the current's always positive. The voltage is positive from 0 to 2. So we have positive power in the region of 0 to 0.2 seconds. This is when the inductor is absorbing energy. Then current stays positive, but voltage goes negative, so power becomes negative from t 0.2 seconds and greater. So here we have negative power. So from 0 to 0.2 seconds, power is positive, the inductor charges up. Past 0.2 seconds, V times I is negative. That means the inductor is releasing energy back into the circuit. And so what we'll find is We have maximum positive power at 58.6 milliseconds. We have maximum negative power at 34.1 milliseconds, which seems to correlate very nicely with these two regions we're seeing here. We would expect positive power for less than 0.2. We'd expect negative power for greater than 0.2, and that's exactly what we get. As for energy, once again, is 1/2 Li squared. Again, we can take this term here, square it, multiply together, and then what we're going to get, then multiply times 1/2 times L, 0.1 Henry, and what we're going to get is this will be equal to 5t squared times e to the minus 10t joules, and we'll find that this is equal to 27.1 millijoules at t equal 0.2 seconds. So once again, take the derivative, set it equal to 0, look for the maximum, and not surprisingly, it occurs when you are at the maximum current, and that's when we have maximum power, or pardon me, maximum stored energy, 27.1 millijoules. So this is a good exercise in just in terms of going through and looking at how we can do these calculations and seeing how these correlate to our expectations. Do we see maximum energy at maximum current? Yes. Do we see positive power and negative power at the places where the voltage times the current is positive or it's negative? Yes. So, no real surprises here, just a useful exercise to show once again how this device is working, how the inductor works. Now let's look at another example, something slightly different. And this is a useful example just because it illustrates something that's very useful, a really basic principle in calculus that you learned at the very beginning when you were learning about integrals. But it's useful to do kind of a simple example to illustrate this. What if we had this kind of example? Let's say I've got a 1 Henry inductor. Now I'm connecting that inductor across a voltage source. And I'm going to calculate the current. And here's what I have here. If the current for t less than or equal to 0 is equal to 1 amp, in other words, if I have an initial condition of 1 amp at t equals 0, then I want to find the following currents. I want to find I at 1 second, I at 2 seconds, and I at 3 seconds. So what does my voltage look like? Because I need that if I'm going to calculate the current. Here is what my voltage looks like. From 0 to 1 second, the voltage climbs linearly to a value of 10 volts. Then from 0 to 3 seconds, the voltage drops all the way back down to minus 10 volts. And then I have a discontinuity and the voltage immediately rises up to 3 seconds. And goes to 0. So I rise from 0 to 10 volts, So 10 volts per second is my slope, then minus 10 volts per second is my slope, and I go from 10 to 0 to minus 10 at 3 seconds, then I jump immediately to 0. Now you might look at that for a second and say, Dr. Holman, didn't you say we can't have discontinuities? We can't have a discontinuity in current for an inductor. Nothing prohibits us from having a discontinuity in voltage. That's perfectly fine. So if I want to go through and calculate this, I could do it the hard way or the easy way. The hard way is to go through, take this region, and go through and calculate the different functions for each region, and then write the expression for that function, and then calculate the integral. Because I'm going to need that, given that in this case the current's going to be equal to 1 over L times the integral of the voltage. Or there's a simpler way. The way you learned in calculus is that the integral is just the area under the curve. So I like to just sort of illustrate this here. So the current at 1 second is just going to be equal to 1 over L times the area from t equals 0 to 1 second plus the current at time t equals 0, our initial condition. So this is nothing more than 1 over L times the area of that voltage. And so in this case, this is equal to 1 over 1 times 1 times 10, the area of this triangle here, divided by 2, and that will be equal to 5 plus 1 is equal to 6 amps. So I did this the easy way. Then for the current at 2 seconds, I'm going to have 1 divided by 1 times the area from t equal 0 to 2 seconds plus the initial condition at time t equals 0. So in this case, it's this area plus that area. I'm just doubling this, 5 plus 5. That's going to be equal to 10 plus 1 is equal to 11 amps. And for t equal 3, I at 3 seconds will be equal to 1 divided by 1 times the area from t equals 0 to 3 seconds. Once again, plus my initial condition, I0. And in this case, I have 5 plus 5, and then this will be negative area. It's below 0. Minus 5, so this will be equal to 10 minus 5 plus 1 is equal to 6 amps. So I just kind of like to do an example like this just to illustrate that quite often for these problems, depending upon the function, you don't need to go through and figure out the actual function itself that describes this and then take the integral. You can just actually look at it, and if you can just calculate the area using simple geometric methods, you get a much simpler solution. So once again, just a simple example of the kinds of ways, the kind of mathematical manipulation you can do, both with inductors and of course with the capacitors as well. All right, so having looked at this, next time we're going to go look at capacitor and series and parallel combinations of inductors. So we saw for series parallel combinations of capacitors how we combine those together. Can we do the same thing with inductors? Absolutely. And let's see how they work mathematically when they combine.